So if you already decide which kind of the sensor you try to combine together, you can find me anytime or email me to get the sensor, or you can buy your own, okay? But you need to make sure that under the 4,000 NT dollars budget, okay? So here, I would like to finish the time domain truncation. So just I see. Yes. Okay. Okay. Sure. Okay. Okay. So the truncation will be like the window. This is a truncation window. So I just truncate here. So capture the rest part. But however, in the frequency domain, you can find originally this is the I say what is that? For the overlap area, this is the effect of what? If I have the overlap in the frequency domain like this one, because of what? Yes, this is the aliasing, okay? And combined with the effect of the truncation. So maybe this is just a very simple the calculation of the multiple. Also, actually, you can get the result of the response in the frequency. But I would like to say the resolution will be decreased in the frequency domain. So we just demonstrate example here. Okay, so you can change the different component. I just use the 100 and 110, or maybe you can use the 200 and 210, or something like that. Okay. But someone would say, Professor, if I use this example already here, let us to show you again. If I only have the truncation of this, but sometimes if we try to extend the duration of the sampling time, I mean, I try to extend as larger of the big T, right? So, Professor, you said that with the big T, I have a higher resolution in the frequency domain. Right, it is in the theory, this is right. So sometimes someone would say, if I have the zero, I mean padding the zero in the end to extend. So something like this. I already have this data, but I try to extend the total length. So the rest part, I use the zero data to padding. This is what we call the zero padding. Okay. Can I get much better result from this kind of the zero padding? Okay, I would like to say, yes, in the theory, you may increase the resolution in the frequency domain, but however, the actual content in the frequency is the same. You not gain any frequency domain. Okay, so actually in the practice, if you try to use the zero padding, it's just like the interpolating between the already existing point, like this one. Interpolating. Okay, no more extra information actually. Okay, so here I already have the zero padding example for you. So I think this is the same. Okay, you can find the data here. Okay, this is a zero padding. Okay, the original signal is the blue one, and the red one here, this is the truncation, and the rest is the zero padding. So actually, you can gain much extra information because the red and the blue one is still different. It's still different. Okay, so I would like to show you in this demonstration about the zero padding. Okay, so I think this is just the topic for the signal processing in the beginning. Okay, so for the next half hour, I would like to show you the other very important issues of the signal processing. The first one is the filtering. So if you already understand the time domain and frequency domain spectrum, so here this is the frequency. So for example, right now I have a frequency like this one. So if I have the window, I mean, if I have a window here, let only this pass through. The other, delete. This is what we call the low pass filter. This is the window that the signal can pass through. The other, delete. Sometimes we use this kind of the low pass to fill a very high frequency noise. Only contain the low frequency part. Inversely, of course, we can use the high pass. Only high frequency pass, but the lower part frequency delete. Or we can use the band pass for the specific range of the frequency domain. And of course, the band stop. This is the same idea. So in the MATLAB, I think you can check the filter. There's a lot of the function you can use for the filtering. But somehow, I would like to say, this is the perfect window, right? Here, this is the perfect window. A perfect window with the very sharp stop length, stop or the pass criteria. But somehow, in the practice, we just only try to mimic the perfect, but we don't have some of the problem of this. For example, if I try to have a very beautiful sharp window, but in the practice, I only have some dribble. This is what we call the dribble here. And this is the stop transition band. Okay, and this pass band, stop band. So we need to understand in the real world, there is no perfect filter. Perfect filters mean like this, but somehow we only have this kind of the filter. Okay, and for the filter, there's divided two kinds of the filter. One is the finite impulse response. The other is the infinite impulse response, FIR and IIR. Okay. So what is the difference between these two? I will use the very simple flow chart for you. The first one, FIR, is just a very simple idea of what we call the moving average. The moving average. I use the X1, X2, X3, X4 and maybe you have a moving average with the equal weighting. So I just get the average of these of these 4 data and get the average with the result. This is the FIR filter. So for example here, YN is the answer for the XN, X1, X. Okay. So this is what we call the moving average, using a 4-point average to output. This is the FIR. But what is the IIR? Much complex. Okay, you need to do the moving average first. It means that this is FIR first. And then you get YN. But however, you need to use the autoregressive to consider the YN minus 1, minus 2, minus 3. It's like the recursive procedure to get into and have a new YN. So this is what we call the forward and like the FIR, and this is what we call the recursive procedure. So IIR is much complex for the calculation. But however, compare these 2 filters. Sometimes we need to think about it, the advantage and the disadvantage. Okay, also IIR is much complex, but it has a good advantage of the nonlinear phase. It has the limitation of the nonlinear phase and the non-stable and oscillate indefinitely. Okay, FIR guarantee a strict linear phase because this is much simple. Okay, and sometimes it is very stable because simple and stable. But however, if you use the IIR, sometimes you may need much lower filter order than the FIR if you try to get the very perfect response. Sometimes in the FIR, you may need 2 or 3 orders to make this perfect filter. But sometimes FIR, because this is a very simple calculation procedure, so you need maybe several orders to get the same result compared to the FIR. So I would like to show you the limitation and the advantage between the IIR and the FIR. Okay, so I think you already know that the efficiency is IIR much higher. Okay, but however the stability is the FIR is much better. Okay, so you can compare this chart for the detail. And for the MATLAB, okay, you can type this filter design and analyze tool. You can create your own filter. Okay, just as I said, if you try to have a much higher order, then maybe they will be sharp. Okay, if you have a lower order, maybe it's like this one. Have a higher transition frequency range, but sometimes this is much stable and easy to do. Okay, so depends on your decision. You can choose the low pass, half pass, band stop. Okay, you can choose the IIR, FIR by yourself, but of course there's a different kind of the type of IIR and FIR. And of course, you can use your order, okay, and with the specified range of the frequency you try to as a criteria. Okay. So this is the filtering toolbox in the MATLAB. So, but I think maybe you need to install the module of the filtering design first in the MATLAB. Okay. For the filter, is there any questions or problem? I think there's. I just showing us the simple idea. But for now, right now, I would like to say we're trying to get into the real world. Get into the real world. For the previous example, you can find this is the sinusoidal signal. But however, in the real world, we would like to say this is the time vary. For the previous, this is a time invariant spectrum, means that repeat again. But in the real world, this is the time varying spectrum, means that lower, higher, and a much higher frequency, actually. So how can we do and how can we interpret this kind of the time varying signal? For the previous Fourier transform or Fourier analysis, there's some of the limitation. Okay, so the first one cannot provide simultaneously time and frequency localization. Okay, what does that mean? It means that if you try to look at the time, you cannot specify maybe the 1 second that have a sum of the frequency of what? Maybe 5 Hertz. You cannot, because in the Fourier transform, you need to take care maybe at least a length of the signal and get the average spectrum. So I would like to say for the previous, this kind of the signal for this is the 0 to 1 second. For this 1 second, I have maybe the 5 Hertz signal component. But I cannot say in the 0.5 second, I have the 5 Hertz or the 3 Hertz component. I cannot say that because this is the limitation of the Fourier transform. So this is the first one. And sometimes this only can be used for the time invariant or stationary signal. For the time variant and the non-stationary, it is not so good to apply the Fourier transform. Okay. Sometimes if I have a discontinuity or this sharp corner signal, sometimes the Fourier transform it is not so appropriate to deal with for this time. So how can we deal with this time variant problem? Extended, we can use the short time Fourier transform. It is based on the Fourier transform, but just look some of the very short time spectrum. For example, here, I just see this is the whole signal I'm trying to see. But I use the very short window to look at the signal. And then repeat and repeat again. Okay. For example, if I use this, I try to look at here. Okay. And the next, maybe I can use the much smaller window and look the different time signal again. So here you can find, I would like to say, this is the result from the typical frequency time spectrum. The x-axis is the time, the y is the original amplitude. But however, if I can use this to the frequency domain and the time domain, you can find here. This mode window, just as I said here, the yellow window is the very, very small. What happened? What happened? We just say that if I have a very small window, this is a signal, okay? So this is the DT, and this is the DT. So if I have a very small length of the signal, what happened?
Resolution in the frequency domain is not so good.
Yes. Okay. Someone not take the recall of this. Okay. So I just say that for this DT, you can determine that the highest frequency, but actually you can find only half, right? Okay, so this is because of the Nyquist frequency 0. But for this, you can find this is the T, and for the data, okay. So if you have a smaller length, means that your resolution decrease in the frequency domain. So you can find here. Okay, I have a small window like this. This is in the time domain. So here I have a time domain here. This is a T. So you can find here, this is a T inverse. But if I have a larger T, you can find here the smaller inverse of the T. Okay, so I get a big picture for you. This is a very large T and a very small, very large T and very small. Okay, so you can agree with that, right? Okay, but I would like to say for the short time Fourier transform, you need to evaluate your requirement between the T and the T minus 1, T inverse. Okay, because if you try to look at a small t, means that you only understand the short time, but very rough spectrum in the frequency domain. Very short time the window in the time domain, but very rough, I mean the low frequency resolution in that time. But if you have a large, here like this one, large time domain, you can find a very good resolution in the frequency domain. But however, just as I say, this is the average in this very big time duration. So this is the what we call the trade-off. So you need to find the balance. If you look at very short time window, you may lose the resolution in the frequency domain. But if you look at very large window, okay, it is fine. But this is just a very large time window. So just as I say, this is only for the sinusoidal, for the invariant time variant signal. If you have a different time variant signal, this is just the average. Okay. So here, this is the what we call the Heisenberg or the uncertainty principle. The trade-off dt df, the multiple result larger than the inverse of the 4 pi. Okay, so means that this is the conclusion. You can find the dt or df very, very small at the same time. No, you cannot. You cannot. Okay. So this is what we call the trade-off at all for the spectral analysis. But however, I think right now you can find this is the case of the short time Fourier transform. You can choose the window size you want, or you can divide it into the different time spectrum for the analysis. Okay, and for the extended, I would like to say the wavelet transform is try to also do this kind of the analysis in the different time and the spectrum. So you can find here they use this. This is our short time Fourier transform. The grid at the same size, but for the wavelet analysis, they try to compensate some of the trade-off problem. So in a very low frequency, I think they try to see the whole spectrum. But in the very high frequency, they just analyze a very short period of the time. Okay, so I would like to say this is the composite with the wavelet transform. Okay, so if you try to look at the low frequency spectrum, maybe you need a very long, a long time period. If you try to look at a high frequency spectrum, maybe you need a short window length. Okay, so you need to change. So I will go through that formulation again. But I would like to say for the wavelet, it is just like the decomposition of structure from the low frequency to the high frequency. Okay, so sometimes you may generate like this one if you use the wavelet analysis. So the first one is the original signal, the red one. This is the original one. So the first component you can find here, this is the lower frequency to high frequency here. So you can find with a different spectrum, you may have a different component. Okay, so here you can see the higher frequency is like the noise. And this is, I think, in this three is the basics pattern of the spectrum for the original signal. Okay, and I think maybe some of you already heard that Hilbert-Horn transform already, and then this is another method for the time frequency spectral analysis, especially for the very short period time of the variant. Okay, so if you can find this is the difference Fourier and the wavelet and the Hilbert transform. So using the HHT, you can much concentrate very what we call the intro wave, very change the waveform change very in a very short period of the time instantly. Okay, but I think HHT is much different. They use the empirical mode decomposition at first. Okay, and they use and have several spectral in a Hilbert transform. So here you can find this is the result. Okay, for the first part is a higher frequency, and for the second part is a lower frequency here. Okay, but I would not to have a very detail of the using this kind of the method. Okay, because it's take a lot of time. So you can find in the MATLAB already. They already built in the MATLAB for the maybe the wavelet and also some of the extra module for the HHT. Or you can learn from the double E department for the advanced signal processing class. Okay. So maybe we have 5 minutes. I would like to have a very quick conclude of the sampling. That's what we call the data acquisition. So already you know that we're trying to convert the analog signal to the digital one. Okay. So here you already know that the time aliasing. So for the red one, actually maybe red one is the 10 Hertz. So what is the minima sampling frequency we should use? If the signal, I already know that this is the 10 Hertz. 20, yes. Okay. But in the practice, if you use the 20 Hertz, you may get a very ugly signal. So somehow we may use the 10 times of the original signal. So for here, I would like to use the 100 Hertz sampling frequency. So after the sampling, you can get a very perfect, very smooth curve compared to the original one. So this is in practice, we're trying to do that. So I would like to say there are 3 RS in the data acquisition. This is very important part. The first one is the time resolution. Oh, time resolution. Oh, sorry. I would like to show you in a very quick. The first one is the rate we just show you. So you need to use at least twice of the signal as hertz. This is the what we call the Nyquist frequency. Okay, so remember this is the time aliasing problem. Okay, so I would like to go to the back. We're just talking about the range. The sampling in the X or in the time domain. But however, if you try to quantify the amplitude of the original signal, you can see we cannot use the continuously measurement, right? Means that we cannot have this kind of the maybe 12 volt and 1, 2, 3, 4, 5, 6, 7, 8, 9. Again, 1, 2, 3, 4, 5. I would like to say in a very simple idea, how many digits of the precision you can get in the real world. Because for the continuously signal, means that the amplitude is continuous. So this is the infinite length of the precision of the digit. But in our PC, we only have the finite space for the storage. So how many digits of the precision we can use? This is my question. This is my question. Sometimes you can find the 6-bit, 3-bit, or the 10-bit, or up to the 24-bit. Please, you can find the next time and tell me what is the difference of this. I give you a hint. This is the 2 power 24. This is the 2 power 3. So means that you only have the A for this. This is the A level for the quantity for the quantification of the amplitude. Okay. So if we have any further problems, so we can keep continue with this in the next week. And please remember, we have the midterm exam in the next Friday, and for the May 30, we have we will have a site visiting. Okay. See you next week.